Now, let's take this information and let's review, because we have looked at this in another presentation, the normal function of the interosseous muscles. In this discussion, I am not specifically breaking out the dorsal from the volar interosseous muscles. I am combining it together, and therefore I am referring to interosseous muscle function. I've taken the anatomical illustration and superimposed upon it solid lines which represent, in my opinion, the dominant power of the interosseous muscles. In one way, you can think that the dominant power is always proximal, because as the muscles insert, the pull or the force is always going to be distributed proximally before it's carried distally. But the solid lines for me represent the dominance of the interosseous muscles in pulling through the transverse fibers as well as pulling through the oblique fibers. Here the transverse and here the oblique. Because the fibers of the dorsal interosseous muscle are interconnected, then obviously there is going to be tension delivered more distally. But specifically, because of the pull here with the oblique fibers, there's going to be transition of power through the conjoined lateral bands to the lateral band. And additionally, because the interosseous muscles insert into the dorsal apparatus proximally, part of that insertion power is always carried through the lateral band. Something I think that is important to remember is that on the ulnar and radial aspects on both sides, the interosseous muscle must always share its power of insertion between the lateral band, the transverse fibers, and the oblique fibers. On the radial side, however, the lumbrical muscle doesn't really do a lot of sharing. It goes more directly into the lateral band. And so there's a greater influence of the lateral band on the radial side. For that reason, I've created a dotted line here that's much thicker than on the radial side when the lumbrical is present. But if you just back away from this illustration, you can appreciate that the power of the interosseous muscles, both the dorsal and the volar interosseous muscles, has a significant influence throughout the dorsal apparatus. Now, in a previous session, we've talked about how important the lumbrical is, and that the interosseous muscles are not always the most active to extend the interphalangeal joints. That is very true. But we also discussed how resting muscle tone can provide a viscoelastic force to influence the balance of motion even when the muscle itself is not actively contracting. So the simple presence of the interosseous muscles with tone, in my opinion, have an influence in balancing digital motion. So the interosseous muscles remain, even though the lumbrical muscle is a significant contributor, the interosseous muscles remain a significant influence on digital motion. Here I've colored this ulnar side with green to suggest that the influence on the ulnar side is shared. On the radial side, there is perhaps more concentration from the interosseous muscle into the proximal fibers of the dorsal apparatus. I don't really know that, but there is some logic in my mind to assume that. Now we're returning to a schematic drawing that you may have seen in other parts of this series that have been presented earlier. The red will always represent the extensor digitorum communis and its influence. The blue will represent the interosseous muscle influence. This small orange structure represents the interpalmar plate ligament. And the lumbrical muscle is represented by green into the lateral band, always assuming we're looking at a lateral view. And this pink, bright pink, represents the passive structure of the oblique retinacular ligament connecting and influencing the PIP and DIP joint motion. In this illustration, we now want to consider normal interosseous muscle function. We want to consider primarily the blue in the illustration. And this is a schematic drawing, so you need to imagine how this would move in the normal anatomy that's very fluid and flexible. In the normal finger, in the position of MP joint flexion and IP joint extension, the interosseous muscles are the primary MP joint flexors. I would like to repeat that. Metacarpophalangeal joint flexion in this position is primarily being accomplished by the interosseous muscles. Unfortunately, for some reason in the past, this posture has often been referred to as lumbrical plus, assuming that the lumbrical muscle is flexing the MP joint and extending the IP joint. In my opinion, that is not correct, and the term lumbrical plus for this position is actually not correct. This is, however, correctly called the intrinsic plus position because the interosseous muscles are flexing the MP joint primarily, and the lumbrical muscle is primarily, but not alone, extending the interphalangeal joints. So if someone in the future asks you the primary role of the interosseous muscles in the human hand, I would no longer answer ab and adduction, although they certainly are functions that only the interosseous muscles can accomplish. I would say their primary role is metacarpophalangeal joint flexion because they are indeed powerful MP joint flexors. If you would put one finger of one hand in the palm of your other hand and wrap your fingers around that one finger. Now squeeze that finger just as hard as you can. And what you'll feel is you will feel the interosseous muscles pulling your MP joints down into maximum flexion. You won't feel the profundus on the tip of your finger doing all the work. You'll feel the power of the interosseous muscle as it contributes to your grip strength. The interosseous muscle is very important for normal grip strength, and this is occurring by a pull of the interosseous muscles more directly through the transverse fibers, because the transverse fibers are a more direct line of pull when the metacarpophalangeal joint is in flexion. The oblique fibers certainly are receiving some power from the interosseous muscles as well, and certainly the interosseous muscles are assisting in interphalangeal joint extension. But it would be very difficult for there to be equal power distributed to the transverse fibers and the oblique fibers simultaneously. And it's my belief that the transverse fibers are getting the core of the power, with only secondary power being delivered more distally. So, PIP and DIP joint, because they both move together, the extension of those joints is being created by a secondary power contribution from the interosseous muscles in concert with both EDC tension and lumbrical power. The oblique fibers, in my opinion, in this position are secondary in receiving power from the interosseous muscles. However, when the metacarpophalangeal joint is in extension, the line of pull of the interosseous muscle as it contracts is a more direct line into the oblique fibers, and therefore when the metacarpophalangeal joint is in extension, the interosseous muscles have the ability to have a more direct influence to help with interphalangeal joint extension. Now I say primary is PIP joint extension, and that is true because the central slip insertion ends distal to the PIP joint. But as we learned in a previous session, during full finger extension, it's not the central fibers that carry the most tension. So it's really the oblique fibers and their contribution in the entire proximal movement of the dorsal apparatus that is assisting with finger extension. That means that it's not just PIP joint motion that's being created, but it's both PIP and DIP joints simultaneously. In this position, the transverse fibers of the dorsal apparatus have moved to their most proximal position. I shouldn't say most proximal. They could move slightly more proximally during hyperextension of the MP joint. But they are nevertheless in their proximal position near the axis of the MP joint. Therefore, in full finger extension with the MP extended, the interosseous muscles cannot have a very effective or efficient influence on the transverse fibers. And these fibers then are not actively flexing the MP joint. They are providing some tension, and I believe are the main contributing factor which prevent MP joint hyperextension in the normal hand when we just extend our finger. So the transverse fibers, even though perhaps not active, are providing, I think, some viscoelastic tension to assist with the balance of motion. The secondary influence, I think, of the interosseous muscle contraction is the transfer of power to the lateral band. Remember, on the ulnar aspect, it's sharing power, and on the radial aspect, it's also sharing power. So power into the lateral band is being created by the influence of the interosseous muscle contraction. So in addition to the power at the PIP joint and into the entire dorsal apparatus, there is some direct power to the DIP joint to assist with extension. And this is a contribution to lateral band tension on both radial and ulnar aspects. Now, I said earlier that the transverse fibers of the dorsal apparatus and the tension from the interosseous muscles prevent MP joint hyperextension. This is so easy to envision because we know when the interosseous muscles are not active that the MP joint tends to hyperextend. If the lumbrical is present, the lumbrical has just enough power to prevent that, but over a long period of time, one can see that the lumbrical really doesn't have that much power to sustain that, and usually a claw position will present late if ulnar palsy has been present for a long period of time. So in the normal finger, when we extend, we stop with the MP joint at neutral. I believe because we're meeting tension of the interosseous muscles. Take your hand and place it flat on the table. Extend your fingers so they lift slightly off of the table. That's very easy. Then try to bring your fingers into hyperextension at the metacarpal phalangeal joint. You not only feel tension of your extrinsic flexors, but I also can perhaps imagine the tension against MP joint hyperextension itself, which must be those transverse fibers. But one of the problems is when the metacarpal phalangeal joint is in a position of hyperextension, the extensor digitorum communis has moved as far proximally as possible until it is now tethered or held back by the sagittal band fibers that are attached to the volar plate and will not allow it to go any further. In other words, or another way to phrase that is, the entire dorsal apparatus, along with that extensor digitorum communis, has moved as far proximally as is possible and cannot move any further. That means that in this position, when the interosseous muscle contracts to supposedly pull through the oblique fibers to extend the finger, it simply cannot do so because the dorsal apparatus is already as far proximal as it will go. A contraction of the interosseous muscle can't move it any further. Therefore, it would be accurate to say when the metacarpal phalangeal joint is in a position of active or passive hyperextension, the interosseous muscle contraction cannot be mechanically effective to fully extend the interphalangeal joints. This is exactly why, in the presence of ulnar palsy, for example, when the metacarpal phalangeal joints are hyperextending, that it is extremely common that the interphalangeal joints are not able to extend and thus develop adaptive shortening and subsequent flexion contractures. Perhaps the most complicated function to explain is that of the interosseous muscles during normal finger flexion. I just said when the finger starts out and is in full extension that the interosseous muscles are not very effective to flex the MP joints, but that they do prevent MP joint hyperextension, whether perhaps by some active contraction or by virtue of their just viscoelastic tension. So it would be appropriate to say that the interosseous muscles participate during finger flexion. In the beginning, perhaps actively, perhaps not actively, perhaps it's just passive. During the mid-range of finger flexion, perhaps the interosseous muscles are quiescent. But when you reach full finger flexion, and especially if you are in that any range of flexion and you want power grip, the interosseous muscles pull through the transverse fibers for power to metacarpal phalangeal joint flexion. So in this position, it would be possible that these transverse fibers are active and they are contracting to provide power for MP joint flexion. But the confusing point is that simultaneously the oblique fibers are not active and they actually must be allowed to move distally in order to elongate to allow the dorsal apparatus to move over the flex joints as the dorsal apparatus is moving distally. So it would be absolutely correct to say that during normal finger flexion, the interosseous muscles must elongate, allowing distal movement of the allowing distal movement of the oblique fibers. So here we have a very complex arrangement where there may be elongation of certain fibers that receive tension from the interosseous muscles, and there may be contraction through or power through other fibers when the interosseous muscle is contracting. One could say this is very confusing, but I think what it really illustrates is that there is a much greater level of sophistication and complexity of human muscle contraction than perhaps we even understand yet. These oblique fibers must elongate during normal finger flexion. That means that some of the fibers of the interosseous muscle need to be relaxed while others are contracting.